Hi, I'm Jeff Ampramos, and thank you so much for joining me. Today I'm going to be talking about claims regarding A-B testing with Bayesian methods. So there's a lot of discussion and sales hype around Bayesian methods and A-B testing. I wanted to see what actually made sense based on the math versus what was more Martech spin. You might assume from the topic that I'm a mathematician or a very mathy data scientist. I'm not. I help businesses use data to make better decisions, but I usually use this with improving how they use third-party tools versus coming up with my own brilliant models. Um, I happen to have an undergrad math degree from a small university, so I can figure out a little bit of what's going on. Depending on what you want to get out of your time with me, that could be a very good thing. I'm coming at this as a CRO tool user like you, not a model maker. I read hundreds of pages of white papers and research. That's just the stuff I printed out on the top shelf, so that you wouldn't have to, and so that I can see what parts of the claims, what parts of these advantages are backed up by the math, and what might be just more of spin and hype. So let's get started. I'm going to fire up some slides and be right back. Let's start our look inside the Bayesian A-B testing tools with a look at the Bayes method in its most basic form. So the most important thing to understand about Bayes is that it allows you to take information you have that you've used to construct a probability around some event happening, and they call that a prior. And then you're going to observe the result of some experiment, or something happens that you use to update your prior information, and that creates a posterior or a probability of event A given evidence B. And you can think of this as the posterior as the result of adjusting your prior belief with experiment results or an observation. And the easiest way to understand this is probably with an example. So we're going to consider an example where the probability that a patient has cancer if 1% of the community has cancer. Now, before we even get into the other stuff where they take a cancer test and they test positive, this is going to be our prior. So they haven't taken the test yet. We don't know anything about that, but we know they come from a community with a 1% rate of cancer. So we're going to use that as our prior. And we're going to start adding some notations so we can get things into the form we need for the equation. Now, we know they take the test, they test positive, and we can use the information about false positives, which we'll assume that the test maker gives us, and do some calculation to get the terms we need regarding the probability of the evidence, which in this case is this test we've just run, or the fact that they've tested positive on this test we've just run. So event A is having cancer, event B is testing positive, and we run the numbers through our equation. And the one little thing to note is that you're dividing the probability of testing positive if you have cancer, so the thing that we're interested in happening, the evidence that we saw and the event we want to detect, and we're dividing that by the probability of testing positive and having cancer, and plus the probability of testing positive and not having cancer. So all of the ways you could get that result. And in the end, it gives you 20%. And the point here is just to show you the kind of the utility and the power here that you can take information you've got from other sources, previous sources, not related to an experiment that you're about to run, and then take the result of that experiment and combine them to get a result that is hopefully more accurate than just taking your experiment results. Now, the tricky bit around this is how do we represent that outside part, that part that's not our experiment result, it's the prior belief. What are we putting together here? And here, it's the textbook example. I just put the example together. I said this person comes from a community with a 1% rate of cancer, so that's what the prior is. Stick it in. In real life, selecting priors is a major point of contention. So in our example, we might ask questions like, wait, how do we know the rate of cancer in the community? Is this the community, state, region, city? How long ago did this guy move here? Is the rate of cancer in our community a relevant baseline to use for him? Should we be, would it be, if we're going to use historical data, should we adjust for risk factors that this guy has related to what we're testing for? And then to go to the CRO situation, it's, out of all this historical data you have in your testing program, or you gather in your testing program, or kind of in your analytics, what are you going to pull out that's relevant to the experiment you're about to run to help you get a more accurate result out of that experiment? And how are you going to model that? So Bayesians say you're crazy to ignore that historical data. There's too much value in there, so we're going to incorporate it using this method. And frequentists, so that's the word for the kind of math that makes t-tests, they say no. There's so much information there that for you to try to go in and find the right piece of information and then apply it, make the right assumptions to apply it the right way to do, to help more than you're going to hurt is not going to happen. That kind of sets up the controversy before we get into examining claimed Bayesian advantages. So we can start by looking at what Bayes will not do, because there's a lot of claims about what Bayes will do. So Bayes will not 5x your conversion rate. It won't make your CRO program immune to methodology issues. It won't whiten your teeth. It won't improve your posture. The hype leads to some misunderstandings, and misunderstanding tools leads to errors. So not a great situation to just be bombarded like that. So for now, let's look at some claims that are at least plausible and see what kind of truth we can underpin there or not underpin there. Bayes very well might be easier to explain to stakeholders, be more suited to CRO applications, generate results more quickly, be less prone to common errors. These are very open to interpretation. So, let me know what conclusions you reach, what you think of my perspectives. Ask questions, say hi. You've got my Twitter address there. You've got the event hashtag, and I'm going to have a post there, that URL on my website, so that kind of links related to this, kind of extra points, anything I mention or that you're curious about, I'll have there, so that we don't, all of the links will be there in a clickable format, and I'm not going to put links in here and have you copy them down. Looking at the solutions we reviewed, we mostly looked at the VWO model because it's well described in a 2015 white paper, and it's a good foundation for Bayesian testing methods. Optimizely has a more sophisticated approach, and they've also got a pretty good white paper about it. But that more sophisticated approach requires a few more concepts, which makes it a bit less less useful to us today as an introductory model. So if people want, let me know, and I might do a follow-up. Google Optimize doesn't have, or at least I couldn't find, a white paper of the same kind of detail level that I saw with VWO and Optimizely, so I couldn't get into that model in the same way. And I've also included Agile A/B tests by Georgi Georgiev of Analytics Toolkit, who's also speaking at the summit. And he's a vocal and thorough critic of Bayesian CRO tools. His product includes something that I'd call a t-test on steroids for CRO professionals. And he makes the point that, you know, a lot of these Bayesian claims of how great Bayes is are, yeah, it's great if you compare Bayesian methods to a t-test that, you know, we've been using for 100 years, but there are more kind of modern improvements you can do with t-tests and with other methods that aren't Bayes. So I took his tool into account as well as a non-Bayesian example of a specialized modern tool for CRO purposes. The argument behind this claim is that stakeholders have one overriding question. They want to know, what is the chance that the thing that we're trying out is better than what we were doing before? So what's the probability the variant is better than the baseline? And the argument continues that Bayesian methods make it easier to answer that question. And they do this by outputting a joint probability distribution of the variant and baseline's conversion rate. So let's quickly look at how they put that together and how that's used to answer that question. So here we'll start with the probability distribution of the variant. And we've drawn it a special way called the density function. And the height of the curve represents a relative probability of the curve B of the conversion rate landing in that the spot under that part of the curve. So high above 10%, bigger probability than low above 25%. If we want to know a probability of the conversion rate being in a certain range, we can take the area cut off by that range. So we take the area above 8% under the curve, and that ends up being 80% of the area under the curve. Now we know that the probability of having a conversion rate greater than 8% is 80%. The important part from a Bayes perspective is that we have a version of Bayes that works with probability distributions. So we can take the earlier version we used and replace our probabilities with probability distributions. We have a distribution for our prior based on historical data, old experiments we've run, campaigns we've run. Excuse me. We're going to have a probability distribution based on our experiment results. Similarly to the way we had before, it's going to be based on a version where we assume the prior is true and a version where we ignore the prior. Now, again, we're going to update our prior with our experiment results. We're going to get a posterior. In this case, the posterior is going to be a probability distribution. So one way to think about this is this term where you assume the prior over ignoring the prior, to some extent is the degree to which the experiment data matches the prior that you had going in. And then the whole equation kind of becomes the prior weighted by how much your experiment data matches the prior. And a good way to understand this is a visual explanation. So here we've just graphed some kind of fake historical conversion data from old campaigns, old experiments, and then we're going to bring back our experiment result distribution. And the next step from a Bayes perspective is to create a prior distribution from this historical data. So that's going to be our red line. And we're going to remove the historical data because we've got what we want for it. That historical data is now represented by the red line. That's our prior. And we run our experiment, and the results of that are represented by the blue line. And together they make a purple posterior line, which these distributions should be smoother, but don't worry about it. What's important is that the red prior comes together with the blue experiment result to kind of come up with something in between. And this isn't mathematically sound, but you can kind of conceptualize it as a red prior and the blue experiment result. You kind of average them together to get that purple posterior. Now, the next step is to do the same process with the baseline conversion rate. And once you've got your baseline conversion rate distribution and your variant distribution, you put them together into that joint probability curve that we talked about. So we have a good way to look at that I'm going to call up in just a second here. Much better. Here is our joint probability distribution for the variant conversion rate on this axis and the baseline conversion rate on this axis. And what this graph is telling us is that the likelihood at any given combination of conversion rates. So the chance of the variant being 8% and the baseline being 6% is very high versus the chance of the combinations in this purple area where it's very, very low. So we can see from this that, you know, there's the variance performing better, but we haven't answered that question we're supposed to be answering about what's the probability that the variant does better than the baseline. So I'm going to add one little thing to this graph and we'll take another look. So all I did here was add a surface, flat surface, going through where the variant and baseline conversion rates are equal. And what we can figure out using that is anything on the side of the surface where the variant has a higher conversion rate and under our joint probability distribution surface is the probability of the variant beating the baseline. And anything left on the other side of the red surface is, and underneath our joint probability distribution, is the probability that the baseline will have a higher conversion rate. All right, we've shown that we can get the probability of a variant beating the baseline from that joint probability distribution, and you know, that's pretty useful. That's kind of what we want to know. Let's remember what a t-test tells us. So the frequentist approach, the t-test, generates a p-value. So that's a summary metric. That's, you know, kind of a good way to think of it. It's kind of like a lead score, but instead of taking downloads and form completions and key pages to get a how good is this lead number, we're taking means and sample sizes and standard deviations to get a how often would the variant do this well if we assume the variant isn't any better than the baseline score. And then we figure out, you know, if the p-value is low, that means that the variant not being better than the baseline would be weird. So the variant probably is better than the baseline. Subtract the p-value from 1 to get the, if we ran this experiment a bunch of times, this is the ratio of results that would show that the variant does better. That's technically what this shows. Now, we realize that number is actually a pretty good stand-in for the probability that the variant does better. And we're not about to go down that rabbit hole of what it actually means with stakeholders. So the math is different, but the Bayesian methods allow you to generate p-values and optimizely reports p-values. Frequentist methods can estimate there's frequentist ways to find probability distributions, and you can answer rather handily the question, what is the probability of this variant beating the baseline, as long as we're willing to avoid getting into weird hypothetical debates about what exists but can't be known and what doesn't exist but we're allowed to guess at. So, you know, if Bayes or frequentist easier to explain is down to your opinion. There's a lot of heated debate, but really it looks like it's more hype, or interesting to philosophers than it is CROs. You know, we're going to explain our results in ways that make sense to the stakeholder. Frequentist and Bayesian methods can pretty much approximate whatever the other one can. You know, the ease of explanation isn't about the underlying math. If we're talking about, you know, what the underlying math is when we're trying to present results, we've probably lost the plot, right? So we should be looking at the tool UI giving us documents and numbers that us and our stakeholders can understand as far as what's easier to report, more than the math a few levels down. Up next, our next claim, Bayesian approaches, are they better suited to CRO? This claim is largely based around optional stopping. So if you're not familiar with the optional stopping issue, it's based around if you're trying to maintain accuracy, you can't just take a t-test you can't just go into your experiment, take a t-test, and if the result is significant, great, end the experiment, and if not, keep going. If you do that, that'll increase your error rate quite a bit. So kind of a quick parallel example is the chance of getting heads. If in 4 weeks I flip a coin, that I have a 50% chance of getting heads. The chance of getting heads, if every week I flip a coin, and if I get tails, I keep going. If I get heads, I stop. By the 4th week, when I flip my coin, after that, there's a 93.75% chance that I've gotten heads. The impact on CRO is significant. So if we peak 5 times, and one thing to note here is peaking, you can go look at the results. The thing is, if you actually take a test and end the experiment if you hit a certain level, but let it keep going if you don't, then you are increasing the error each time you do that. So if you do that 5 times, you're essentially tripling your error. That would mean that this claim holds up in the sense that the CRO use case is definitely at odds with t-tests. We want to, you know, if we see results that are very convincing, we want to get that advantage and move on to the next experiment as soon as possible. If we can't do that, right now we either waste time and money running the experiment longer than necessary, we risk a higher error rate and kind of do optional stopping without the error control around it, or you have to figure out your own optional stopping error controls and apply them, which is not trivial. So an issue with this as a Bayesian claim, though, is that Bayesian methods are not immune to optional stopping issues. The tools reviewed apply optional stopping error controls automatically. So the tools let you do optional stopping. It's not really inherent to Bayes, though, and it's actually led to a bit of a misunderstanding about, like, oh, Bayesian methods are immune to optional stopping, which is totally not the case. But the tools that we looked at have controls built into it. So one issue is that the methods for that control aren't fully disclosed, so there's that concern that you can't really explain 100% or know 100% if something weird happens, exactly how it's figured out. So by allowing us to call an experiment early, and controlling for the error that can come from that, the tools we're looking at do allow us to get results faster, arguably not so much because they're Bayesian than because they're controlling for the error in a built-in fashion. So there's another area where they can speed up getting results, and with the optional stopping, if we want to stop the experiment early, they've controlled for the error. There's another area around stopping rules, which is they identify certain circumstances where they recommend that you can call the experiment at that point. So looking at VWO system, again, for simplicity, they use something called a smart decision feature. So instead of looking at a p-value, they look at something called an expected loss. And what that is essentially is, on average, what do we expect to lose if we choose the wrong variant? So it's a way to reflect both the probability of making a mistake and the cost of making that mistake. So in that sense, a 10% chance of getting it wrong and causing a 0.01 drop in conversion rate is a 0.001 expected loss. At the same time, a 1% chance of a 0.1 drop is still a 0.001 expected loss. So big chance of a small problem or bigger chance of a, or smaller chance of a bigger problem ends up with the same expected loss. We are going to look at our joint probability distribution again and get a visual feel for this. So just give me a quick second. So we're back with our probability distribution graph and our surface showing where the cutoff is. So we remember that the probability is based on the area underneath that curve that's on the variant or the baseline being higher side of the straight surface we put in. Now what we're going to say is, if we pick that variant, because that's the one that looks better, not just what's the probability, what's the area under here, but for each area under there, each spot under there, we're going to cross index, we're going to say, okay, so for this probability here, where the baseline is 8 and the variant is 6, we have this much probability, and our conversion rate would drop by 2% in an absolute way. So we do that for every part of the curve that's under the curve on the baseline side, on the wrong side, if we're going to pick the other variant. And that is how we figure out an expected loss. We'll jump back to the slideshow. And if we accept a higher chance of choosing the wrong winner, because essentially we're saying, instead of waiting for more of my probability curve, my probability surface to move to the variant side by gathering more data, I'm saying I'm okay with that chunk that's over there on the other side, as long as, you know, I can leave more probability over there as long as the cost to my conversion rate is not that high. So I'm cool with making the wrong decision as long as it doesn't cost me too much. I'm going to tolerate that higher probability of getting this wrong, because I know, I at least think that it shouldn't cost me too much. So yeah, this is faster, and it's automated, and it's a lot nicer than you looking at it and calculating it every day or whatnot. But it's not magic. It's trading a little bit of accuracy for speed, and that's okay as long as when you look in at your results, you've read your docs and you know what a smart decision is and how to interpret that. And the results here are faster because of a metrics change, essentially, which, you know, is kind of data people should be pretty recognizable, because we've gone from using essentially a p-value or a probability on its own to using a metric that's a bit more suited to a business decision, which is like, you know, we're willing to get it wrong as long as it's not going to cost us a fortune, or as long as the cost of getting it wrong is less than the cost of just moving ahead. Optimizely and Google Optimize have different stopping rules, but similar principle. They're actually different from each other in VWO, not from just the stopping rules and from the error control side, So it would be an interesting comparison, but just not that we do not have the time. I do want to touch very briefly on prior selection, though, because that's a really central point. So VWO uses uninformative priors. We talked earlier about you got to come up with a prior kind of based on what you think the information you already have to use as a starting point for your Bayesian analysis. So one school of thought, and VWO in their white paper discusses using this one, is that the prior is just going to be a starting point. And as we accumulate data, the impact of that is going to disappear. Google and Optimizely use data experience to create a informative prior. Now, again, you can think of that as a starting point, but instead of it trying to be neutral and just conform to whatever the experiment data ends up being, it's trying to function as a head start. So it's trying to kind of guess a few things based on everything that Google and Optimizely know about CRO and get us a little closer to the end of the experiment by making a few assumptions off the bat. Now, it's essentially a bet, but if we think about the bet, it's, at least for the top tools, right, that we looked at, it's the top experts with access to tons of data, and we're betting that they're going to use that, to what they've learned from that, to speed up our experiments by making the model more specific. And they're only going to trade away the flexibility that just doesn't apply to CRO experiments. Now, so you can kind of worry about assumptions and stuff depending on how like mathematically rigorous and how your thinking is set up. But the truth of it is that unless you've got significant internal testing resources, this is a very compelling offer. So to wrap up, the Bayesian tools that we examined have advantages for CROs, at least when they're compared to traditional t-tests. Excuse me. The issue is that with built-in optional stopping rules and controls provide faster results without the accuracy issues of kind of guesstimate optional stopping. The thing is, there's frequentist tools like Agile AB that also have error control for optional stopping. So the advantages may have more to do with this idea of adopting for optional stopping and doing what's sequential testing, or so using sequential statistic methods that just more accurately reflect the reality of how we use tools in CRO. So there are advantages, but they're not magic. So the assumptions that speed things up can cause flexibility, accuracy, or both. Unusual experiments might throw the tools more easily. So if you're testing something that's got a really high conversion rate, you might want to ask your vendor rep, is there something I should know about running this kind of, like 80% conversion rate test, or any tips, or if you've got very weird data coming out of something. It's like there's an argument that these tests, because of these assumptions they've made, if those assumptions aren't right in that particular case, might get thrown off more easily. There's also a bit of a cost in terms of understanding how the tool works, both for us and stakeholders. A lot of, if not most people in business have seen a t-test and heard about it and been exposed to it to a varying degree at some point. This is kind of new stuff, and there's a certain degree of you needing to get to understand it, and a certain degree of stakeholders, and also a certain degree of they don't, depending on how rigorous, how much you need to vet these tools, you don't know 100% of what's happening inside the tool. So I think the advantages are worth it for pretty much any organization that doesn't have the resources to start building its own CRO tools and building its own modeling. My takeaways about that, though, are you want to read your docs, and you want to make sure you know what the output from your tools means, and you want to know how the stopping rules work. You want to know when this thing says, hey, use this variant, what does that mean based on the data that you have? Consider taking t-tests and comparing results. Different methods that have the same result is a very powerful indicator. So if you're using the Google stack, that's what I generally use, so I know, I'm sorry to not be more platform agnostic here. You can check out DaVinci Tools by my friend Stéphane Amel, and that is a free Chrome plugin that actually you can take t-tests very easily right from inside your Google Analytics. And you can also use a modern frequentist tool like the Agile AB tool and compare results from that. So, if you can have two different models pointing the same way, that's a good sign in terms of accuracy. Thanks so much for watching. I had a great time putting all of this together, and I hope I'll have a chance to talk to you about it. Please get in touch on Twitter, use the hashtag. Come by if you've got a longer question, go to the link I gave and leave a comment on that post. And really, I appreciate your sharing your time with me, and please enjoy the other great speakers and talks that are here at the summit. Thank you so much. Take care.